The finite square well finally makes its entrance. It's ironic because we started with the infinite square well, and now to end the chapter we end up with the finite square well. So let's see if we can use our intuition about what we learned along the way to solve this problem. What we want to do is analyze the odd bound state wave functions for the finite square well, which, if we recall, v of x, the potential for the finite square well, is equal to negative v0, 0, for x between negative a to a, or shortcut notation like that, and 0 for a outside of, or rather for x outside of a, the width of the well. So, no big deal there. Nice definition. Some authors prefer just to shift this thing up and create a barrier. It all depends on how you want to approach it. Mathematically, it doesn't make much difference, but let's continue. We wish to derive the transcendental equation for the allowed energies and solve it graphically. That will be fun, so hang in there till the end. And then we have we wish to examine the two limiting cases. And we've done this before with the delta potential. The subscriber PDF is posted if you want it. But nonetheless, what we have here is we need to look at the well that gets really narrow and shallow, and we need to look at the well that gets really wide and deep, which I think we know what happens with that one. So is there always an odd bound state? Well, that's very context dependent, and we'll have to figure that out. Let's check it out. So the authors of this book, which link in the description if you want it, were really clever in making us prove some theorems that would be very useful for us regarding the types of solutions that are allowed for different types of potentials when we started off the chapter. 2.1c specifically references that if you have an even potential, then the solutions will take the form of an even or an odd, because of the linear combination that we have, the linear combination abilities that we have. The textbook drives us through the even solutions, and now we have to do the same for the odd solutions. So be aware, that's what we want to do. How we report the odd solutions due to symmetry is we're only going to report on half the well. And what I mean by that is we're going to go from 0 to a, and then for x greater than a. And then we note that we're going to be the negative with the negative variable change, and that's what's highlighted in the green here. So if we go to the other side of the well, we're going to be negative d sine of Lx, and then we'll be from 0 less than x less than a. So x is negative between 0 to negative a. And then here we would be negative f e to the negative kappa x, or positive kappa x, for x less than a. So that's what this green term represents. It's just a really nice way of reporting it, and we report for the top half of the well. And what I mean by top half is 0 to a. So just be aware, a little shorthand there. And the reason why we do this is because of the fact that the theorem allows for these solutions to occur. We know that if we find the boundary conditions and systems of energy on one side of the well, it's going to be symmetric to the other. That's why we do it this shorthand way, and we can run through the rest of the calculations now. We do have to use our boundary conditions, which state that we need the continuity of the wave function at x equal a. So here we see we get, just plug in a, we're good there, no problem. We need to take the derivative of this statement and plug in a again, so we have the continuity of the derivative at a. And we see that this just gives us a L factor, no big deal. We bring down a negative kappa from the chain rule. Again, no big deal. Plug in a after the fact, and this is what we get. As we see here, we have two equations and two unknowns, d and f. Let's get rid of them both by taking the continuity of the derivative and dividing it by the continuity of the function at the barrier. And we see that when we do that, the coefficient d cancels on the left-hand side, coefficient and the exponential cancels on the right-hand side. Beautiful. And we see that thanks to our trig functions, we get cosine over sine, which we know is cotangent, and it all collects so nice and neat here. This is where the next round of math will get messy, and what we need to pay attention to is the fact that we have L and K, which came as a solution to the time-independent Schrodinger equation within those particular regions. This shows a problem because L and K both have an energy term in here, and if we have two different variables that are with the same variable of need, L and K, and the variable of need being E, we need to do a substitution on here, and that'll be our next step, and get ready for some algebra. Alright, so following the textbook's notation, we go ahead and let the argument of the cotangent be z, so z equals LA. If we solve this for L, we get L equals z over A. Cool, no big deal. But we're still left with the fact that we need to solve this thing for z and kappa, both of which are variables of something we want. So let's write kappa in terms of z and see if we can plug this into a graphing software and, streamline this through. Recall that the definition of L came from the Schrodinger equation as such, squared it to get rid of that square root, leaves us with this beautiful thing. And also realize that kappa was very, very similarly defined. So here, what we want to do, put it all in one big square root, and note that the trick we're going to use here is adding by 0. What I mean is that I could add a constant, or I could add a entity, so long as I minus the same entity, and then I could go ahead and simplify down. And that's what we do. Add an L squared minus an L squared. If you want to work backwards from L, realize that 2me is kappa right here. So either way, kappa and L are related to one another. We're just trying to showcase how to find the interrelation so we could substitute out appropriately. So moving forward, if we plug in L squared on the positive side and just leave the negative L squared on this side, what we see here is that this substitution will eventually, when we fact or FOIL out the 2m with the e and v0, we get these fractions here that cancel. Wonderful, we like that, get rid of them, no big deal. Now we have a function with kappa relating the potential and the variable of interest z, and now we can simplify this down even more. So again, color code L we found was z over A, and now we just algebra our way through the rest until kappa can be a function of z. So factor out of 1 over a squared, you see that forcing factor has to be put in the numerator there, and then you see that the square can be taken outside the square root, no big deal. Here we see again, we have a substitution that the book uses. Here's how they got that substitution, and this is how we get z squared, or z0 squared. This whole thing is z0 squared. Again, if we factor out a z from both sides, we have to do the forcing factor down here. So take that all out, and then you see that the square and the square root, we get z over A equals the square root of this entity squared, minus 1. And this is probably the easiest thing that we could do in terms of numerical solution, because now we have two things that are simplified down pretty close. And what the benefit of this is that now you can look at end behavior, or the asymptotic behaviors, which is what they asked us to study, pretty easily. So let's go check that out. Well, a final round of simplification. We solved for kappa, so we plugged it in on the right hand side. This was what we found. And notice that we get a cancellation of z over A on both sides. Wonderful! And we get this nice, what we call a transcendental equation. There is no closed form solution here, so we have to use numerical approximations, graphical solutions, all the tools that we have. That cotangent makes this thing very difficult to find closed form solutions, so we just don't do it. We just stick with the numerics. That being said, even numerical things have behaviors that we can talk about. And the wide deep well means that A, because if the width goes wide, that means A gets really big. And if we want deep well, that means that V0 gets really big. So we say that A and V0 go to infinity, and what we're looking at is what is the characteristic of our variable change. So we know that Z0 has V0 in it, and so we see that this is going to blow up too. And if that blows up, what this does to the whole function is it shifts the graphed up towards the asymptotic lines of pi, 2 pi, 3 pi, and it shifts the intersections to those points, and that's what we're looking for. So this thing gets shifted to the asymptotic lines of the negative cotangent, and since we're looking for where they intersect due to this equivalence here, that's where we're going to find our answers. But notice here that with a function like this, only the even values will survive the intersection. So if we pair that with the odd values for n that we got on the even solutions, we now have the full set of solutions for the infinite square well, the ISW infinite square well. And that makes sense. If I get infinitely deep, that's the same thing as having the having the potential at infinity at the boundaries. That's really cool. So that one kind of makes sense. Conversely, if I have a narrow shallow well, or if I'm looking at the variables at A, the width getting very, very small, or the potential, the shallow part of it getting really small, that means that one of those two things is going towards 0, and if that's the case, our z0 approaches 0. But if we approach 0, then we don't intersect an asymptotic line or the negative cotangent, and that's why we have the stipulation that z0 has to be, if z0 is less than pi over 2, there are no odd bound state solutions. We don't intersect the graphs anywhere. So that's a minimum threshold there. And if that's the case, if we set this minimum threshold equal to the z0 barrier, or the z0 constant right here, and funnel back all the way into v0, we have a v0 bound state condition here, where we have v0 is less than pi squared h bar squared over 8ma squared. Again, more algebra. This means that we have no bound state solutions when this potential is the case. So we're not always guaranteed, and this is the one way to guarantee that we don't have one, is by setting a potential less than this. A lot of talk about graphs, so let's go actually see what I'm talking about. Alrighty, so here's the graph, and I want to note here that this is the right-hand side of that transcendental equation. This is the square root of z0 over z squared, and we have minus 1. Here I set z0 equal to 10, which is highlighted here with the interception of 10 at the x-axis. If the cotangent is 0 and we solve, this would be 10 right here. No big deal. We like that. Easy enough to deal with. What I want to point out here is that we have the asymptotic line of pi, 2 pi, 3 pi, and so as I said, as we get really as A or V0 go to something really big, this thing here gets shifted up towards the asymptotic limit, and so we see that we get really, really close to the pi's. And that's what gave us those energy state eigenvectors or eigenvalues and the linear combinations thereof. So here for 10, if we have our z0 at 10, we have 1, 2, 3 solutions. Okay, and it is pi, 2 pi, 3 pi. So we're seeing that we get kind of one every periodicity of this, and they're going to be at different locations for however many we deem. But 10 giving us 3 is something to keep in mind. Also, if we get really small, this blue line shifts down here, and we skip intersecting with the cotangent red line, and that's why we can say we don't have bound state solutions. I do have a Desmos link for this, so you can go and tinker with it all you'd like. It's pretty simple to make, but if you want that link, comment and I will gladly send it to you, because these numerical solutions are bound to come up again. No pun intended. That is a steady state solution too. They are bound to come up again. And not only in this class, but in several other classes where you just have to use numerical methods on these equations. They're not always nice, they're not always pretty, but you can definitely get good results. See ya next one. Thank you for watching, and as always, until next time, happy learning.